And I think there is a problem with pizza yet. So, do you want to open the discussion for all the talks of today? So, okay. Okay, then I think there's, yeah. So questions to all the speakers of today, just shoot. Who starts? Okay.
Actually, let me ask Piero about the large changes in the escape. Yeah, let me ask Piero about the large changes in the escape fraction. I mean, given the range over which you're talking about here, 3 to maybe 4 to high redshift, physically, what would be driving that? What could drive that?
Actually, the range it goes to get that flat gamma, which I showed from the 11 alpha.
Yeah.
That starts at redshift 2. Okay. At redshift 2, we know there are already a lot of quasars. So you don't want galaxies to overproduce UV.
Yeah.
So the escape fraction for galaxy must be small. At high redshift, it must be very high. So from redshift 2 to redshift 7, you must go from a fraction of a percent or less than 2% to 20%. What might drive that? Well, I mean, people have been thinking, and we had the idea that the escape fraction from the dwarf galaxy is high, for example, because of feedback, etc. So then as the dwarfs start to dominate the elusivity at every time, you get a larger escape fraction. But from the theory point of view, it's impossible to predict escape fraction.
Yeah, it's just, you look at galaxy samples that go, particularly where we have the data that's on a common basis from, say, redshift 3.5 upwards. The properties don't appear to be particularly different. So it's hard to imagine the escape fraction is then
changing so much. But if it's 20% on redshift 2, you overproduce the background by a large factor. So something must be happening there.
Yeah.
I just don't know what and why.
But maybe something's happening between 2 and 4, and after that the galaxies have pretty typical and common, whatever, that it doesn't change very much at earlier times.
More doubts, questions, provocative statements.
Will you be able to constrain the escape fraction with JWST by using H alpha versus Lyme alpha?
Yeah, you certainly have more sensitivity with that. There's a lot. I think there are options, but I haven't looked at that, so personally I just don't have a good feel for that.
Did you want me to say something about this? Where?
Yes, actually.
Okay. I have a figure. I could just show it. Okay. And then maybe, Brant, did you want to say something? Why?
Well, I was just thinking about the presence of these, the possibility of high redshift quasars, like what Piero was talking about. And there are 2 additional constraints we haven't mentioned. One is the Sultan argument, and it seems like the amount of time in that epoch of the universe is short enough that that's probably not a strong constraint. But you can imagine doing what James has done with galaxies, with black holes, and Ford model, given these quasar luminosity functions at high redshift, where is the typical low luminosity quasar black hole at redshift 5 today at redshift 0? And I don't know the answer to that. I was wondering if anyone thought about it. Martin.
Is it a response to this?
Now for quasars, it's quite a bit more complicated because you have a duty cycle. So it's not a one-to-one relation. And if anything, we think the duty cycle is going up. So to come up with a model where sort of the luminosity function evolves very little, or maybe even rising to higher redshift, is not that difficult. But there's an extra parameter there, and you can just look at your bright galaxies. So there are enough bright galaxies with an AB magnitude of -22 that could harbor a big enough black hole to do that. So I think there's no problems in terms of numbers of beings. They're already well-developed structures. And to predict the duty cycle, there's quite a bit to go to do that robustly.
So James,
Yeah, sure. So You just asked about, you said, your intuition was that most of these objects at high Z that might be contributing to reionization, these faint things are going to end up in clusters. And I think,
in heavier halos than the Milky Way.
Yes.
So in the typical 10 to the 13 or 13.5, not in the gigantic clusters.
yes, so this is right, so that's true, but that doesn't mean there won't be any progenitors in the local group. So this is just an exercise where you go to Z of 8, Millennium 2, you look at everything that has a halo mass bigger than 10 to the 9, and you ask where it ends up at Z of 0. And so it's within the virial radius, so bound descendants in the virial radius of each of these systems. So in an LMC, it's basically just the LMC. So in a 10 to the 11 halo, it's basically 1 to 1. In a Milky Way, we expect, about 10 or so. And then if you go to a Fornax style cluster, it's a few hundred. And so it just depends on the question you're asking. Of course, there's a halo mass function that's going the other way. And so if the question, if you want to know where are the descendants of first light dwarfs that were contributing to reionization, this is basically where there are. Since we live in this halo, this is a good place to start. And of course, these are also close, but then you have to go fainter to look at them.
So my point was, when you do take into account the halo mass function, where indeed the trade-off is from the simulation, you should be seeing where most of the contribution comes from, and absolute numbers.
Yeah, in absolute numbers. I don't remember we did this exercise at some point, I don't remember but it's actually pretty flat. My recollection is it's actually quite flat per number density where you expect them to live, because there's just so many fewer of these than these. But I can't remember in detail.
There is another constraint that we looked at. I don't think I need that, but I'll use it anyway. Another constraint you might be interested in is, and we checked that, is the contribution of faint high redshift AGN to the X-ray background, right? Because, these are X-ray sources, hard X-ray sources. Their radiation is going to be redshifted down to Z equals 0. Now, a large fraction of the 2 kV background today is resolved by known sources. So you have to ask, what is the contribution of the Gianlongo et al., if you want, faint AGN to the unresolved component of the X-ray background today? And if you take the emissivity that I put forward in one of those plots and extrapolate to high redshift, you get a contribution that, depending on alpha or X, the ratio between the optical versus X-ray radiation, it's about 50-60%. So basically that means that those faint AGN are providing, if those points are correct, are providing a large fraction of the unresolved soft X-ray background today. Okay? And it's okay that it's a fair fraction. What you don't want is, of course, to overproduce it, because otherwise you have too very many faint AGN. That's why I cannot go above those numbers, because if I go higher than Gianlongo redshift 6 or so, I overproduce the background. And that's why I have to ionize a 5.7, not 6.5 or 7. Otherwise, too very many faint AGN, the background will be too high today to be consistent with observations.
Okay,
Just to Frank, the last one, if it says there.
Okay. I'm trying to reconcile what Piero is saying and what Martin is saying. Martin wanted to resort to quasars because you wanted to explain the variance in the PDF, the broadness of the PDF. If you go and you resort to many low luminosity AGN, at some point that variance goes down again. So I think there's going to be an optimal limit where you have the right number density of quasars to both get in touch. So if you translate that number, you quoted that you need to have variability in the UV flux to explain the data. If you translate that number in a bias parameter, how is the UV flux bias with respect to the density field? Do you have that number? I think that gives some useful insight.
I think the number he quoted are basically the Gianlongo numbers. And I think Sandy just asked the question. So far we have just done a toy model, and I answered Sandy's question. Said you need about 3 times the vicinity. Then you need there for a very simple model, but there's a good reason to bring it down. So we're working at the moment to basically make the two consistent. But we don't need it at higher. Basically, we say we need half with a 5.9. can't rule out the galaxies. You don't need the fluctuations at lower redshifts because the beam will pass as much. We need at this particular redshift, we need at least half, and probably the Biolongo may just do, in which case it's then up to you if you want to extrapolate even further to higher redshift, or if you want to say then the galaxy stays open.